I've already given a number of presentations to the IES, and so I decided this time to give something completely different. And I decided to try to give an overview of what us as a group are doing at the IES or have been done in the IES in the last 3 years, which I now is a choice that I regret because it was massive work. We should have never tried to start from the beginning. But on the other hand, it has been an amazing satisfaction to see how many nice, interesting things the people that I'm so lucky to work with have been able to do. So I hope I will give you a fair overview of what these guys are doing with me. And in order to do so, I would like to divide the presentation in 3 different groups. So at the beginning, the question that I would like to ask, to try to explain, is why I'm interested in vortices and unsteadiness. So the talk will be on external aerodynamics and boundary layer flow. And I would like to explain you why external aerodynamics and why boundary layer flow are related, and why in the way they are related there are vortices and unsteadiness, which are the key of what I'm working with. And this unsteadiness mostly comes from the boundary layer flow. And so I will present you the research on the boundary layer to show you how an unsteady and complicated can be the flow field that is experienced by bodies which are immersed in the flow. And then I will present you external aerodynamics, which basically means what happens to these bodies which are immersed into the boundary layer. So to start with the vortices and the unsteadiness, we just take whichever wing you want. So for instance, if you take the wing of an airplane, but you can also take the wing of a bird if you like. It will be the same principles. They have similar wing plans if you like, and similar sections. So we can take one of these sections and imagine that the section of the wing is immersed in a uniform flow. And we have the 2 major forces, one vertical force, which is the one that allows the bird to fly, or the airplane, and the drag, which is what we have to overcome in order to move forward. Now, what it is important is that the ratio between the lift and the drag somehow represents this angle, which basically means how efficient is your foil. So how much drag, how much do you have to pay in terms of drag in order to achieve the lift that you need. So the lift over drag is actually a measure of the efficiency. You can redraw everything just in normalized units, and you say, the velocity is 1, so these 2 becomes 2 coefficients, and we can say the same argument. We can say the left over drag coefficients are a measure of the efficiency. Now this is interesting because basically all we do is about solving these equations, either numerically or we can actually do experimentally and observe that this equation is always satisfied, which basically means that the mass by the acceleration is equal to the 2 forces which act on the body, the pressure forces and the viscous forces. So basically it's F equal ma. So it's this simple equation. And this simple equation must be solving the boundary conditions, which means that how fast is the airplane going, but most importantly is which is the shape of the wing or the shape of the section. So if we know the shape of the section, we know the boundary condition, we solve these equations, and we can find the velocity and the pressure in every point around the wing. Now, if we make it non-dimensional, same exercise we did before, it is very interesting because what happens is that now this velocity is a non-dimensional velocity. It's the ratio, for instance, from the velocity wherever you are and the velocity at which the airplane is flying. So this is a non-dimensional value, this is a non-dimensional value, and a non-dimensional value. And what you observe here, there is only one parameter that comes out, which is the Reynolds number. That means that basically, whichever wing you have, either the airplane or the bird, the differences between these 2 fluid mechanics is only due to the difference in Reynolds number, which might not exist. So if the Reynolds number is the same, it doesn't matter if you're very small or very large, if you are in the water or in the air, the fluid mechanics around the wing will look exactly the same. This is important because it reminds you that basically all the flow field will depend only on the shape of the foil and on the Reynolds number, on nothing else. So it doesn't matter, again, even as difficult it could be to imagine that the fluid mechanics around the wing, which is that big, could be the same fluid mechanics around the wing, which is enormously big. So look at these 2 parameters. So we have the efficiency of the foil, and we have the Reynolds number. Okay? what we actually find that if you look at most of the profiles of the wings in the world, you will actually have that very high Reynolds number, you have very high efficiency. But if you go lower Reynolds numbers, the efficiency drops down terribly. And so what happened is that if you are in this region, low Reynolds number, which is typically the one of the insects, of the birds, they actually struggle to fly. While flying for an airplane is very easy, because the efficiency of the foils is much, much higher. Okay? So this is the key aspect of these talks. What happened is that at this condition here, which is the typical condition which is investigated by aeronautical departments, they have attached flow around the wing. And what they know is that they have to prevent that the flow separates from the wing. That's what they have to do. All right? So all of the typical traditional aeronautical fields is about trying to keep this flow attached around the foil. But if you go at this region here, that doesn't work. The flow will always separate, and there's nothing you can do about it. If you don't separate, in fact, most likely you will not generate lift. So the way that the insects and the birds generate lift, so what they need to stay up, is actually to make vortices. If they don't have that the flow separates from the wing and generates a vortex, the birds will never be able to fly. Interestingly, potentially, you can actually exploit the same mechanism also at higher Reynolds number. Of course, the efficiency that you find will be lower than the efficiency that potentially you have with fully attached flow. So this is not, in principle, a very smart way to generate lift. But it does have advantages. In fact, this kind of vortex flow at high Reynolds number is adopted by sailing yachts and by delta wings. Now, delta wings, for instance, are when you have a jet fighter, which has jet fighters are designed. You might remember like a triangle. This is a delta wing. Now, the reason why they use it is comes from different aspects. One of those is that if they have to go ultrasonic, then they need to have this shape. But there are other reasons which makes these two applications in common, that when you have that the angle of attack alpha is keep varying, in this case I'm saying that it's varying with time, but the point is that if you have that the angle of attack is keep changing, now this way to generate lift is very good, because this airplane stands up only at a small range of angle of attack. But these two can actually generate lift at a much wider range of angle of attack. So if the condition of the angle of attack is changing, maybe rapidly, the airplane that adopts this kind of fluid mechanics will actually feel much less perturbation and will actually have a much more steady lift. So let's go for the first step, which is the research on boundary layer. So now what I'm interested in is how do we generate this large variation in the angle of attacks? Why are they so important to us? Well, they're so important because if you have a wall, like this one could be the seabed in the tidal channel, or it could be the free surface of the ocean if you go sailing, or it could be whichever other surface where you have the wind or the water passing by. What happens, as long as you have the same Reynolds number, is that you actually see exactly the same picture. All right? So what you will find a mean velocity profile on time as a time average, but instantaneously the velocity will keep changing. All right? So if you look why these velocities keep changing, and if you try to see inside this flow, you will see these flow structures. These are called Hairpin vortices. And basically what they are, they actually show you that the fluctuations inside the boundary layer, they're not random, but they're actually coherent structures inside which have very specific features. They're basically made like a C shape like this, where the legs are attached to the wall, and then the head of the hairpin is transported downstream. And they have an angle which is about 45 degrees with the, and so they move like this. So these vortices, so the point is that the vortices already exist. So when you have an airfoil which is immersed into a boundary layer, this airfoil will experience the impact with these vortices, or the interaction with these vortices. So it's not only the vortex that are generated by the wing, but also the vortices which are interacting because they come from the background flow, which is already there. Now that one was a DNS simulation, and just because it's nice always to show some validation of the simulation we perform. In this case, you can see the velocity, and here you have the distance from the wall. So this is this is roughly 0 in terms of the distance from the wall, and this is the head of the top of the mast of the sailing boat, if you like. And you can see that because the Reynolds number is the only parameter that we have, actually there are many people who are trying to do this simulation, and you can find that there is reference data from 1999 that we match quite well. But very importantly, if you want to be sure that your turbulent structures are correct, so these vortices are correct, you cannot just take the mean value. So what you have to do is actually to look at statistics. So here again, this scale is not logarithmic, but it represents the same. So here you're 0, so here you're at the wall, and here is the head of the mast of the sailing boat, if you like. What you have to do is to look at the first order statistics. So this is basically the standard deviation of the fluctuation of the velocity perpendicular to the wall in the plane horizontal, but not in the direction of the flow. And this one is the standard deviation of the fluctuation in the direction of the flow. And 1, 2, 3, these three statistics, as you can see, fit very well with experimental data as well, with DNS data. And this one will be the kinetic energy, and these are basically the Reynolds stresses. And you can see, very interesting, this is something that my students always wonder, is why the Reynolds stresses actually have a minus in the front, and the reason is because they're always negative, in fact, which is the only curve which is always on the lower side. So the Reynolds stresses, this U prime V prime, or U prime V, because the average of V doesn't exist, so it doesn't matter. So U prime V prime are the cross product of the fluctuations in the streamwise direction and in the vertical direction. If you make the time average of this cross product, these are the Reynolds stresses. Now these are very, very important, which is this curve here, because what they do is actually they generate friction on the surface of the boundary layer. So the friction here is due mostly by this cross product U prime V prime. So what is our research? Well, one of the aspects that we are interested in is what happens if we now have roughness here. And this is interesting, for instance, if you look at the seabed and you want to know how will looks the boundary, your stream in the sea in a tidal current based on the roughness that you have, then you need to find a way actually to model the effect of the roughness on the flow. And this is what Nicola Speranza is doing. And one of the aspects that he's particularly interested in is we know that the velocity profile, I don't know how many of you will remember the logarithmic law, but you can actually find out that the velocity in a non-dimensional form increases with the logarithmic of the distance from the wall in a non-dimensional form. Then you add a constant value, that's not being very important, but if you have roughness, you need to subtract another constant value. So the effect of the roughness is basically to translate up and down your entire velocity profiles in non-dimensional units. So this component here represents a parameter which is due to the effect of the roughness. But how does this parameter vary with the Reynolds number is not known, and it's one of the aspects that Nicola is interested to work on. And we are particularly interested on this one because if you think that this one could be the boundary layer on the ship, what happens is that at the stern of the ship, the Reynolds number is so high that it is impossible to perform any numerical simulation or any experiment. So we need to find a way to make an experiment and to identify how much is this value at lower Reynolds number and then extrapolate it at higher Reynolds number where we cannot measure it or simulate it. And the other aspect that Nicola is interested is what happens when you have a combination of micro micro and micro features. So you have the roughness, but on top of this, you also have, for instance, welding on the ship, or you have a major rock on your seabed. Okay, so I thought that Nicola would have given his own talk very soon, so I'm not to present his results, also because his results are particularly difficult from the mathematical point of view, so you need to show a lot of equations which didn't fit with today, so I'm not going to present Nicola's results, but I will present the results of the other guys. And in particular, the other aspect we're interested in, what if you have sort of a compliant surface, so something that is not rigid on the bottom of the seabed, but can move. So for instance, you can have algae or any other stuff which actually is moving when the turbulent fluctuations vary. So the stresses here will keep changing instantaneously and will move these, for instance, algae on the seabed. Now we know this is happening. What we are interested to know is, can we actually design some specific structure on the bottom of the seabed or on the surface of the ship where actually this structure can be so smart to decrease the friction forces that act on it. So what happens is that if you have a flow passing by, you will have flow fluctuations. You have U prime and V prime, the one that I showed you before. The combination of these two generates friction. And you can see that from here. So the friction on this surface, so the force which is pushing this block in this direction, is actually proportional to the Reynolds number, as we said before, but also to this U prime, V prime, to the Reynolds stresses, which, as I mentioned before, has a minus in the front. So what we want to do is to learn about how the flow fluctuates here, learn about the Reynolds stresses, and learn how can we manipulate these Reynolds stresses in order to decrease tau. And just to clarify, if you put an anemometer here, so if you measure the velocity in this point, what you will observe is that the flow will actually keep varying in time, and you will have a mean value. What we are interested in are in the fluctuations, and we're not concerned about the mean value. Of course, in the stringwise direction, there will be a mean value. In the y direction, so in the direction this sense here, there will be no mean value. This is probably a mistake. Okay. Now, once again, if you have that instantaneously, you have an acceleration of the flow here. So instantaneously, this is not just the mean, but it's the mean plus a fluctuation. That means that there is a vortex here, which is passing by. So this accelerated flow in this point is related to the fact that you have a vortex, like this one, which is accelerating the flow in this point. So what we really want to do is to manipulate this vortex. So the question was, what can we do? And actually, what we find out is that if we move this block, in order to have the velocity of the block is equal to the velocity fluctuation of the flow here, all right? So we have that every time this point here is not just traveling at a constant velocity, but it's actually accelerating a bit, we take the excess of velocity and we match it from the wall. So the wall will move by, say for instance, this is moving at 1 meter per second on average, and then for 1 instant we'll go at 1.1 meter per second. Well, we'll take this block and we'll move it this way at a speed of 0.1 meter per second. We'll match the excessive velocity. If we do so, actually what we find is we find 10% drag reduction, which is massive. So what you have to imagine is that, can we actually design a structure such that when there is an acceleration of flow here, which will be somehow correlated with an increase of friction, this material will behave in a way that will accelerate, and its velocity will actually match the excessive velocity here. Can we do this? Right, so the answer is yes, we found out. And the reason why is yes is because of this. It's because if you measure the velocity acceleration, the excessive velocity u prime, and at many time in time, so you have many dots, And for each of these dots, you actually go and see how much was the shear stresses fluctuations. What we find is that they're not just like a circle here, but they're actually along a line. So that means that every time you have an excess of velocity, you do have an excess of shear stress. So this suggests, if you perform some non-dimensional analysis, you will find out that potentially you can actually attach to this block a spring and a damper. And so you actually here you have the equation of this mass, damper, and spring. And this system, if we choose the right mass, the right coefficient for the damper and the right coefficient for the spring, will actually perform exactly as we wanted it to do. So what Thomas is now doing is to run a CFD simulation where it's implementing these boundary conditions into a numerical simulation to provide a proof of concept that this is actually possible, and so that we can actually design microscopic compliant coating which behaves like a spring and a damper in order to decrease the drag of, for instance, of a ship. All right. Another aspect of this boundary layer flow that we're interested in is if you forget about the sailing boats which was here, and we now think about what if this one was indeed under the water, is that if we have waves on top of the vertical structures that we know, there would be the submarine position of these vertical structures. These vertical structures are actually due to the wave. So if the wave is moving in this direction, you will actually have the flow here will be accelerated in that way. But when you are under the trough, it will go backwards. So basically what we're doing, we are introducing inside this boundary layer an infinite number of vortices, which decreases inside towards the seabed. So one of the fantastic things we have here is we actually have, well, Rowan, but also we have the possibility to test this in our flume. So we have a flume which has two paddles at the edge, and so we actually potentially can create a tidal stream and at the same time to generate these waves, and we can measure what happened. And if you measure it, if this is what you did, if you measure it, you find that in fact if you stay and you measure the velocity and the angle of attack on one point in the middle of your channel, you'll actually have the angle of attack, the flow will come, say, from left to right, but it's not just going straight. Because of these vortices, we'll keep changing direction, so the angle of attack will increase and decrease periodically, and the velocity will increase and decrease periodically. And these two curves represent the variation of the angle of attack along one wave period and the variation of the velocity of the flow in one wave period. Now, why this is so interesting for us? Because now we can actually put a body in that position and look at how are the forces, how is the fluid mechanics around this body, which is immersed in this specific condition, so which is actually experiencing the effect of these circular vortices. And here is where we call external aerodynamics. Now, why do we call it aerodynamics and not hydrodynamics? Well, the reason is a bit of a traditional reason. So when we work on just one fluid, so when we're interested in the forces around one body, the forces of one fluid on one body, so for instance either the water or the air, then this is what we call aerodynamics. On the contrary, when we have hydrodynamics, we are considering the fact that we have two different fluids, the water and the air, and their interaction is somehow important for us. But we are only interested in what happens around our body, which is completely immersed by water, and so for this reason, because it's only one fluid, we traditionally call it aerodynamics. There are also other views, but other way to define it, but I think this is the one I chose. What happened if we put this foil immersed inside the flume and experiencing this large flow fluctuation which I described before? Well, this is one instantaneous picture of how the flow field looks like, and this is a measurement. It's not CFD, but it's PID, so it's actually the measurement of the flow. And this one takes from the work of Susan Tully that she has already presented, so I will go very, very quick. because she has already given a very good presentation, which I invite you to go and look on YouTube if you have not seen it yet. Is it on YouTube? Hopefully it is. So what happens is that if you have this rigid body, in particular if you consider this particular instant in time, which is when you have the maximum pressure gradient across the foil, but anyway, it doesn't matter at the moment too much. The key point is that this is one picture in time of the flow field around the body. And what you see here, this region here is a region of very low speed. Actually, it's about 0 speed when it's this color. So that means that actually here, you're now generating a vortex. Now, there are two vortices here that are playing a role. One is the circulation around the foil. So this big vortex, which you normally don't notice, but is the vortex that it must be here in order to generate lift and to bring up the foil. This is the circulation. It's exactly the same as your lift. So there is a linear relation between the circulation and your lift. But here, you're actually generating a trailing edge vortex. So you're actually generating a vortex which is rotating in the opposite direction. So because of this vortex, which is undesirable, this one will diminish the strength of your circulation, and so it will diminish your lift. So every time you generate and shed this trailing edge vortex, you have a drop in the lift. How can you prevent this? Well, one of the interesting things that you can do, you can actually try to use a flexible sails, like this foil, like this one here. So you have a foil like this one, which is not just statically remaining in this position, but when it is the right time, it actually moves up and prevents the generation of the trailing edge vortex, or at least it diminishes its effect, which is what you can see here. So at this time, the foil has moved up a little bit, and the trailing edge vortex has decreased in strength. And so the negative effect on the circulation, which is what you want, has been diminished. Now you can see exactly the same if you take a time average over an entire wave period. You see that there is an entire region of very low speed. So on average, you are always generating this negative counter-rotating circulation. That is something that it is undesirable. While if you look at the wave here, you can see that on average, clearly, the amount of flow going backwards is much less. Now, if we look at the forces, if you measure the forces rather than the velocities, this one is your foil, and we're interested in the force which is normal to the foil in this case. Well, we would have liked to measure the lift, so the one which is vertical, but we couldn't do it. So the only force we could measure was a normal one in this case, in this specific case. So here you see the non-dimensional normal force to the foil, and here you see the angle of attack, which is varying with time. So what happened is that if you have an ideal foil, right, and you look at one condition per time, you will move along this black line. So basically what it means that if you put this foil in this foil rigid in a constant angle of attack of 10 degrees, you have this force. And if you put this foil in a constant angle of attack of 5 degrees, you have this force. All right. Now, instead of having a constant angle of attack, you have an angle of attack which is keep changing with time. So what happened is that now, when you are at this angle of attack, you actually the angle of attack slowly decreases and your force decreases. And then when the angle of attack increases again, instead of coming back along the same line, you come back along this line. And the reason is because you're shedding trailing edge vortices, and these trailing edge vortices that you're shedding are actually taking away most of the lift that you would have had in the other part of the loop. So you're rotating in this direction, which is, you need to be careful because most of the time you see an hysteresis loop, it rotates in the opposite direction. But in this hysteresis loop, it rotates in this direction. If you have a flexible blade, on the contrary, you move along this line. Now, this is very important because the bottom line is that the same geometry, one flexible, one rigid, will actually give you very different load fluctuation. Here, you go from a very low load to a very high load, but if it is flexible, the load fluctuation is much smaller, all right? But even more importantly, because you're not losing a lot of lift due to the trailing edge vortices, is the efficiency which is higher. So the bottom line is that the flexible foils will have a longer fatigue life because it will not break due to such a large load fluctuations, which is periodic every wave. And on top of this, is far more efficient in terms of lift over drag ratio. So this is an interesting application for tidal turbine blades potentially one day. Now the person who is working on this is Gabriel. He's the latest arrival in our group, so I'm not presenting too much about what he's working on now, but you will hear from him very soon. And he's working on analytical models which represents this behavior. Okay, so we have seen what happened if you put a foil in very simple geometry like this one here inside the fluid. Now let's look at some geometries which are slightly more complicated, like for instance a delta wing like this one here. Okay? So this is slightly more complicated because it's three-dimensional. Because it's three-dimensional, everything changes. And the vortices that you generate could actually not be shed, could potentially remain attached to the foil, which is very interesting. This is what you see here. The concept of delta wing is this one. This is your jet fighter, this is your delta wing. And what you see that you're generating a vortex, but the vortex is always there. It's not like a trailing edge vortex that you're generating and this is gone back behind you, would just be dissipated in the wave. This vortex remains here. And it's the same that happens in these guys. If you have a swift wing like this one here, like this bird, you actually have these two large vortices, very similar to the one of the delta wing, which remains permanently attached to the wing. Now, the question we have is, we know a lot about delta wings because they have been used in aeronautics for almost a century, but not on jet fighter. But we know very, very little about this vortex, which is called leading edge vortex, or LEV. We know very little about the LEV around the wings of the birds. And the reason is because we realized that only 20 years ago, we realized that this is the reason why birds are actually capable to fly. Because if you actually make some traditional aerodynamics analysis, you find out that the birds should not have enough lift to carry their weight. But actually they do, because they exploit this fantastic mechanism. So the question we have, which are the differences in the geometry, in the features of these two vortices, by the fact that really what you're doing is simply to subtract the middle part of the wing. So these two wings are identical. You just take away a part of the wing. And is this going to change dramatically the features of the vortex attached to it? These two vortices, you need to imagine them like this. These two vortices are something like this, all right? That's what they do. So you can see like this, like in this picture, or you can see them like this, okay? Now the question is, when you look at from the top, this vortex is actually sustained by this wall. If I now put this vortex on this geometry, initially the vortex is smaller than the wing, but there will be a point where the vortex becomes larger than the wing, because the vortex is always increasing in size, because it's capturing more and more flow the more towards the trailing edge you're moving. So the vortex must increase in size. If the wing is actually decreasing in size, there will be a point where you actually have that the vortex doesn't have the wing below it. The other interesting aspect that we are interested in is it has been found, initially we thought that every time you are managed to have this vortex, you actually have lift augmentation, you increase your lift. But then someone found out that you can have the LEV vortex without any lift augmentation, and we don't know yet why. So this is the work of Rowan, and you can see here these two geometries which I just described you, and she has achieved these amazing results for now, which shows you that the vortex which is generating on the delta wings is actually, in these particular conditions, a dual wing. So you have you have one vortex which is going up to here, but then on the way back it generates a counter-rotating vortex. That's what you find, okay? So this one is a cross-section, sorry, pardon me, I should have probably mentioned before, there's a cross-section at this level of your delta wing. And if you move from A to B, you basically increase these sides, you move from here to here, and this, not much has changed. You see the same behavior. You have this large vortex rotating in this direction. Some air is comes inside from here and rotates in the other direction. If you have a swift though, the first thing which is interesting to observe is that we have exactly the same vortex, which is an amazing result because no one knew how was the vortex on a swift wing at an angle of attack which is not massive, which is probably the angle of so in this case you have an angle of attack of 7 degrees. It means that the wing is moving forward, not horizontally, but with just 7 degrees. Because the vortex is so small, it has always been difficult to measure. It's much easier to measure the vortex when the wing is in this position. So we are the first one who actually managed to measure this vortex when we have a much more reasonable angle of attack, which is the one that we will expect when you actually are cruising. So first of all, we now know which is the shape and the characteristics of this vortex, which are the same as in the delta wing. But more importantly, now we find out that because when you arrive on the section B, actually there is a missing part of the wing, the vortex, which was already large enough, found lack of support from the boundary, and so it basically breaks down and decreases consistently of its coherence. So the coherence of the vortex is lost, and we know from aeronautical experience on delta wings that when this happens, which we call it vortex breakdown, the lift which is generated by the vortex goes down. I don't know what time is that.
It's 10 minutes to.
Ah, all right. I need to go much faster. Okay, so last application. Now, going even more complicated is this shape now. This is a spinnaker sails, which is not only 3D, but is also out of plane. It's very highly cambered, and so it's three-dimensional, it's highly cambered, and also has these two curves which are completely out of plane. So what happened is that we have found with computational fluid dynamics that you can actually achieve this amazing vortex which contributes to about 20% of the lift. If you look at this plot, this comes from numerical simulation which I performed before coming here. You actually find out that the flow comes from left to right, goes around here, starts rotating around the leading edge of the sail, which is a horizontal section of the sails, and then carries on and moves away. So there is some vortex, some flow which is entrapped inside this bubble, and once it's got inside the bubbles, will climb up all along and will come out from the head. So this is what we found numerically, and we did not know if it was true. We were looking for experimental evidence that this was the truth. And here is the experiment of Naval, which has been achieved just a few weeks ago. Here is the evidence we had from CFD. This is one streamline computed from CFD. And these are the streamlines that Naval had managed to measure with PIV, so in the flume, which is the first time ever we have demonstrated that it does exist a possibility to design a shape, a sail shape, which actually have an increase of 20% in the lift, because it can actually sustain a stable leading edge vortex, which contributes to the lift. This one is just a proof of what we're saying. So if you draw a line perpendicular to the surface, so this one is you're looking at the spinnaker in this way. We're looking at a line along this direction here. And what we want to know is if the flow is really reattached after having been around the leading edge vortex. So the leading edge vortex will exist if the flow here is completely attached. And this is what you see here. You see this one here is the velocity. This is negative velocity, means that the flow will go back and the flow will be separated. This is positive velocity, means that the flow is going in this direction, so the flow is attached and the leading edge vortex really exists. And here you see a very large number of velocity profiles measured in many different instances, and the mean value. And you can see that only 5/100 of the samples represents a separated flow. So this is a clear evidence that the flow is attached and the leading edge vortex really exists. So with this, I need really to thank so much all the people that have contributed to this work, which making this presentation made me realize how many fantastic achievements they have already achieved. And also, it's worth mentioning that Qatar has just started, you see here, Qatar has just started for a new, completely exciting project about the vortices which will be generated around the dandelion fruit. Thanks.
This production is brought to you by the University of Edinburgh.